Hi everyone, welcome back. Today we'll be hitting section 10.2 on rational exponents. And if you remember from our work in chapter 7 on rational expressions and rational equations, rational is sort of loosely equivalent to saying we are working with fractions. So we'll start with something of the form a raised to the 1 over n power, then we'll look at a more general form. So for starters, we'll use a let line. We're going to let y equal 3 raised to the 1/4 power. Now, I can take both sides and raise them to the 4th power. As long as the left and right sides are equal, the left side of the 4th is equal to the right side to the 4th. So left-hand side is now y to the 4th, right-hand side is 3 to the now 1st power. 1/4 times 4 is 1. So y to the 4th is worth 3. Now if we go back to our work in section 10.1, then we recall that a 4th root is asking the question, what can I raise to the 4th power to get the argument, the stuff inside? So for example, if we want the 4th root of 3, this is asking the question, what can be raised to the 4th to reach 3? Well, if you notice, when we raised y to the 4th power, we got 3, so y must be our answer. So the 4th root of 3 would have to equal y. Well then, by substitution, if this is equal to y and this is equal to y, they have to equal each other. So 3 to the 1/4 power is the same as the 4th root of 3. My apologies, that should be a little bit smaller, but I still want it readable on the video. So there's nothing particularly special about this example. I happen to use a y and a 3. In general, if we have a to the 1 over n power, that's equivalent to saying we are asking for the nth root of a or a to the 1st. Now here we're going to make a couple of assumptions. We're going to assume that a is in the set of real numbers, and we're going to assume n is at least 2, and n is in the set of natural numbers. So 2, 3, 4, 5, etc. So the next thing they have us work on is simplifying using this property. So we'll start with just 25 to the 1/2 power. So this one is a square root. You can write the 2 in the index if you have a square root. You can, but you're not required to. You can write it with or without it. So this is the square root of 25, which is just 5. So 25 to the 1/2 power is just a plain 5. Similarly, 27 raised to the 1/3 power is really asking about a cube root of 27. So we have an index of 3 there. So if I multiply 3 copies of 3 together, I reach 27. Therefore, our cube root is worth 3. We can also do the same thing with variables. If I have x to the 1/5 power, that's the same as saying I'm asking for the 5th root of x. Where you want to start being careful is where we have sign numbers involved or numbers and variables in the same problem involved. So for example, opposite of 25 to the 1/2 power, Without parentheses, this negative is just floating around out front. It is not part of the base, so it goes outside of your radical. So this is asking for the opposite of the square root of 25, which of course then is a negative 5. We may have something like 7x to the 1/5 power. Similar warning here with the 7 as we had with the negative sign on the last problem. Without parentheses involved, there's nothing that I can do to make that 7 part of my radical just yet. So this is just 7 times the 5th root of x. Alright, so I'm going to give you a couple problems to try. I'll put them up here. After I put them up, go ahead, pause the video, try them out, and play the video. So you're going to try the opposite of 81 to the 1/4 power. We're doing these without calculators, as we will on the quiz and test. Negative 27 raised to the 1/3 power. I'll try negative 8x to the 1/3. And negative 8x quantity to the 1/3. Okay, take a minute, try to simplify those guys out, and go ahead and play when you're done. Welcome back. So our first one, negative was not part of the base since it was not included in parentheses, so this is the opposite of the 4th root of 81. And if I multiply 4 copies of 3 together, I hit 81, so this would be a negative 3. This next one, that negative was in the parentheses, so that is going inside of our radical, in this case a cube root. Cube root of negative 27, I can multiply 3 copies of negative 3 together to get negative 27. The next two, similar looking, one with parentheses, one without. The one without, that negative 8 is just outside the radical, along for the ride, and we have the cube root of x, and nothing else I can do to simplify that after there. The other one, however, with these parentheses, both the negative 8 and the x are under your radical. Bottom of your fraction was a 3, so that turns into your index, and we have a negative 8x underneath there. Cube root of negative 8 is negative 2, however. So we have negative 2 times the cube root of x. So that takes us through the 1/n power. A more general case, we can raise things to the m/n power. But really this will work in much the same way. We'll just have an exponent inside of the radical. Easiest way to see that, power raised to a power, remember your shortcut is to multiply. So I can turn this into a to the m raised to the 1/n power and use the same rules as before, nth root of a to the m. So generally we just cut out the middleman on that one. So they may ask us to do some simplifying. So we'll try maybe negative 256 to the 3/4 power. So there's two things we're doing that. To that, we have a 4th root. Our negative is outside, 256 inside, and a cube inside. Now since we'll be doing this without a calculator, it's definitely going to be easier to take the 4th root of 256 than it would have been to multiply 3 copies of 256 together by hand and then try to figure out a 4th root of that. So I'm going to hang on to this negative, and if I multiply 4 copies of 4 together, we hit 256. You can do that off to the side on your paper if you need to. 4 times 4 times 4 times 4 turns into 16 times 16. There's your 256. So we have negative 4 cubed. So I haven't used this cubed yet. I have to hang on to that exponent, and next I'll just go ahead and multiply it out. So negative 4 times negative, I'm sorry, the opposite of 4 times 4 times 4. So negative 16 times 4 is negative 64. Let's see, what else can they have us play with? 2x plus 1 squared, all that underneath a 7th root is then equivalent to 2x plus 1 to the 2/7 power. So we can move back and forth between the two into or out of radical notation. So I'm going to have you just try a couple of these out. Again, I'll just put them up, pause the video, try them out, and play the video. So you're trying to simplify these without using a calculator. We'll try 9 to the 3/2 power, negative 32 quantity raised to the 2/5 power. Okay, welcome back. First one, square root of 9 cubed. Again, since we're doing these without a calculator, we can either do square root of 9 or 9 times 9 times 9. Much easier to do the square root of 9 first. Square root of 9 is 3. And we hang on to that cube. 3 cubed is 27. Similarly, our other one, we're underneath a 5th root this time, and we have negative 32 squared. Instead of squaring negative 32, we'll go ahead and break it down and work with smaller numbers instead. So 5 copies of negative 2 multiplied together will give us a negative 32. So I have negative 2 quantity squared. Yes, you still need those parentheses. Negative 2 times negative 2, careful here, is positive 4. So the next thing they have us play with is a little dust off of what we worked with in 91 and 93 with negative exponents. So if you'll recall, if we have 3 to the negative 2nd, that was the same as 1 over 3 to the then positive 2nd power, or 1/9. Negative exponents, when there's rationals involved, work very much the same way. If we have a to the opposite of m over n power, that's 1 over a to the m over n power, and you can simplify from there. Here we're of course assuming a is non-zero, since we don't want a 0 in the denominator. Okay, we're squared away pretty well there. All right. So they may ask us to simplify something like 27 raised to the negative 2/3 power. So first thing I want to take care of is the negative in that exponent. So I'll throw that right into a denominator. So now it's 1 over 27 raised to the positive 2/3 power. After that, the problem looks pretty much the same as it did before. So 1 over cube root of 27 squared. Instead of doing 27 squared, we'll do the cube root of 27, make a little number rather than a big number. So 1 over 3 squared is 1/9. All right, so I'm going to give you all a couple problems to try out. So you're going to simplify both of these without a calculator. Opposite of 125 to the negative 2/3 power, and negative 125 quantity to the negative 2/3 power. Go ahead and pause them and try them. Simplify. All right, welcome back. So the first one, the negative was not in parentheses. That is then not underneath our radical. So we have opposite of 1 over 125 to the positive 2/3. So negative 1 over the cube root of 125 squared. Hang on to your negative 1. Cube root of 125 is 5. 5 times 5 is 25. 25 times another 5 is 125. So negative 1 over 5 squared, so negative 1/25. Our second one, this time the negative was inside of the radical. That is going along for the ride then. So this is 1 over negative 125 quantity raised to the now positive 2/3 since it's at the bottom. So that's 1 over the cube root of negative 125 squared. Cube root of negative 125 is negative 5. So 1 over negative 5 quantity squared. So this is positive 1/25. So then we start looking at simplifying when we have rational exponents involved. We don't have any new properties for exponent rules versus what you already knew from Math 93 and Math 95. So if you're dividing with the same base, you keep the like base and subtract the exponents. Multiplying with the same base, you add the exponents. Power to a power, you multiply. All same rules you knew from before. So they may give us maybe 9 to the 2/5 power and have us divided by 9 to the 12/5 power. So I'm dividing with the same base. I keep the base. So this 9 stays a 9. Now it's raised to the 2/5 minus 12/5 power. So that is 9 to the negative 10/5, which is 9 to the negative second. 1 over 9 squared. So this is 1 over 81. Notice that is not the same as just 81. 1 over 81 and 81, two different quantities. That may give us p to the negative 3/7 times p to the 6/7. I'm multiplying with the same bases, so I will add those exponents. So p to the negative 3/7 plus 6/7 power, which is p to the positive 3/7 power. If it's a positive exponent, we leave it where it is. Yeah, let's try one more. So we'll maybe look at 11 to the 2/9 cubed. Power to power, we multiply. So 11 to the 6/9, which is 11 to the 2/3 power. This one, unlike the other one, I can't do any simplifying. 11 is not a perfect cube, so I can't get it out of the cube root. So that's as far as we can take that one. So they do also occasionally have us multiplying with variables involved. So we might have x to the 1/7 by x to the 1/4 plus x to the 5th. So this one, distributive property problem, I have one thing times more than one thing in parentheses. So I have x to the 1/7, x to the 1/4, plus x to the 1/7, x to the 5th. I'm going to start adding fractions. Adding fractions, I do need a common denominator. Common denominator between 7 and 4 will be 28. So I have x to the 4/28 times x to the 7/28. Common denominator between 1 and 7 is 7. So x to the 1/7 is fine. X to the 35, 7's for the other guy. So we have x to the 11/28 plus x to the 36/7 power. I can't do anything with these since they're not like terms. Just like I couldn't add 5x squared and 6x cubed, I can't add x to the 11/28 to x to the 36/7. They have to have not only the same base, but the same power as well. Alright, so let me have you all try another one out. Put your foiling hats back on. X to the 1/4 plus 8 times x to the 1/4 minus 7. So take a minute, simplify that. Okay, welcome back. So we FOIL it out. X to the 1/4 times x to the 1/4. First times first. Plus outside times outside. -7 times x to the 1/4. Plus inside times inside. 8 by x to the 1/4. plus last times last, 8 by -7, -56. And then we're just doing a little cleanup. A fourth plus a fourth is a half. So x to the 1/2 minus 7x to the 1/4 plus 8x to the 1/4 minus 56. So plus a -56, we shorten that. And here I do have two like terms. Same base, same exponent, they are like terms. So x to the 1/2 plus x to the 1/4 minus 56. You can put the 1 in front of the x to 1/4 if you'd like. It's not required though. Alright, they also ask us sometimes to work backwards. So they may ask us to factor x to the -1/3 from 5x squared plus 7x to the -1/3 plus 2. So each one of these has to be worth whatever it was in the original. This 2 I can think of having an x to the 0 power on if I like. So I want it as 5x to the -1/3 times x to the something. When I add -1/3 to my something, I want to get a 2 for an answer. So that would be a 7/3. If you have to write that out to the side to figure that out, that's okay. So -1/3 plus some number has to equal 2, and solve that for n. Add a third to both sides, get your common denominator going. The next one already had a x to the -1/3 attached. We'll leave that one alone. This one, x to the -1/3 times something ending in 0, that would be x to the +1/3. And then we use the distributive property. Each one of these had an x to the -1/3 attached. So distributive property kind of backwards from the way you first learned it. Where now we're making the problem. X to the -1/3 goes outside, so 5x to the 7/3 inside, plus 7, plus 2x to the 1/3. And there is our factored version. And then the last thing we look at in this section is writing things as a single radical. So we start with square root of y times cube root of y, and they want it as a single radical. Well, I can temporarily go to exponent notation to make my life a little bit easier here. So square root of y is y to the 1/2, cube root of y is y to the 1/3. If I'm multiplying with like bases, I need to add the exponents, and I'm adding fractions. Adding fractions, what do you need? Yep, common denominator. Least common multiple of 2 and 3 is 6, so I have y to the 3/6 times y to the 2/6 power. So that is y to the 5/6 power. They did want it as a radical, so I'll switch back to radical notation. Bottom of the fraction is my index, so a 6th root of y to the 5th. We can do that with division as well. If I have, let's say, cube root of x over 4th root of x. Again, I'll go temporarily to exponent notation. X to the 1/3 divided by x to the 1/4. Dividing with the same base, I want to end up subtracting the exponents. I need a common denominator. 3 and 4, multiple would be 12. So x to the 4/12 divided by x to the 3/12. And subtract those, that would be x to the 1/12. Radical notation, so this means we have the 12th root of x to the first, or just 12th root of x. And we occasionally get to do this with numbers as well. I might have square root of 5 times cube root of 2. Same idea applies. Go to exponent notation first. 5 to the 1/2, 2 to the 1/3. Notice here my bases are not the same, but if I want them under the same radical, I can make the denominators of the exponents the same. So 2 and 3, multiple would be 6, so 5 to the 3/6 power times 2 to the 2/6 power. So this means I have a 6th root problem. 6th root of 5 cubed by 2 squared. So that is the 6th root of 5 cubed is 125, 2 squared is 4. So that is the 6th root of 500. That's as simplified as we can get on that one. Okay, so that is all the fun we're having with section 10.2. Let me go ahead and put the homework up. So 10.2, 1 to 57, every other odd. 73 through 105, also every other odd. So if you have questions, please feel free to email me. Otherwise, I will see you for the next video on 10.3. Stay safe, keep your loved ones safe, and hope to see you after this is all done.